Ladies and gentlemen, in this Red Gaming Tentacom video, we're going to be further discussing the PlayStation 4 hUMA technology. hUMA, of course, means Heterogeneous Uniform Memory Access. Now, for those of you who are not familiar with it, I have discussed it briefly in other videos. Actually, to be fair, pretty in-depth in other videos, but a brief explanation of it for this one would be that both processors, that would be the GPU and the CPU respectively, don't actually share different memory areas. So in other words, they can't really distinguish them. For all intents and purposes, they are basically reading off exactly the same memory. This means that you no longer have like two separate pools of memory, and basically you no longer have to copy data from one memory pool to another memory pool. That's a brief summary of it. Now, some of you may be aware that what Liverpool is. Now, Liverpool is the code name for the APU, or the AMD Jaguar / GPU, inside the PlayStation 4, in other words, the SoC. And Liverpool is basically its code name. So, Liverpool has several buses available. I'm going to quickly give you guys a rundown of them, just in case you're not too familiar. First bus is known as the Garlic bus. It's tied directly to the GPU and has full memory bandwidth, 176 gigabytes per second. So that's from the unified memory to the GPU. It doesn't snoop the level 1 or level 2 cache of the CPU because obviously it bypasses it. Then you've got the Onion bus. This does snoop the CPU level 1 and level 2 cache and has 10 gigabytes per second each way in terms of bandwidth. Then you've got another Onion bus. This one is known as the Onion Plus bus. This does bypass the GPU cache and shares the Onion's 10 gigabytes per second bandwidth. And then finally there's the CPU bus. We're not exactly sure what the bandwidth is of this. It's under 20 gigabytes per second, is about 20 gigabytes per second. And once again, obviously that's connected directly to the CPU, to the memory. So all memory addresses are 40-bit. The purpose behind this is pretty simple. This address size allows both the CPU and the GPU to have the same virtual address space. But pages of memory do not need to be both mapped to the CPU and GPU, but also the pages of memory, by the way, are freely set up by the application itself. Now, address space, by the way, is the set of all legal addresses within the memory for applications. So the address space is basically represents the amount of memory available to a program. Now, because of virtual memory, address space doesn't actually have to equal the same size as physical memory. So in other words, it can be more because of virtual memory. And the basic premise behind this basically is that large applications won't necessarily all fit into the actual memory, in other words, the RAM. And therefore, certain pieces will be copied over to, say, the disk drive, and then when those pieces are needed to actually be executed, they will actually be copied back into main system RAM. And so, obviously speaking, there needs to be a deciding factor on how the memory, or should I say, how the data in the memory is actually accessed. Because obviously you've got loads of different buses, and it's important for the right bus to access the data so that the most efficiency is well utilized. Now, the GPU itself, of course, requires a hell of a lot of bandwidth, generally speaking. And so if a particular task itself does require a lot of bandwidth, it will be directly accessed via the Garlic bus. And as we've just spoken, the Garlic bus is the fastest of all the buses, 176 gigabytes per second. And so this will basically force the CPU to access it as uncached memory. On the other hand, let's say the situation is completely and utterly reversed. Let's say the CPU needs to frequently access this piece of memory, in other words, this page. In which case, it'll be actually mapped as cached memory or cached memory, depending how you wish to pronounce it, on the CPU. And as we've just discussed, The Onion is much better suited for this because the Onion bus can actually snoop the level 1 and level 2 caches of the CPU. So in other words, if it's just held on, say, the caches of the CPU, the Onion bus could say, okay, I need to use that, I need to calculate that, okay, now I'm putting it back. Now, there are multiple different types of buffers on the PlayStation 4. We're going to discuss the easiest one probably to understand first, and that is the RO. That's also known as read-only. Now, read-only is pretty simple. If you guys are familiar with files at all, you'll understand basically the premise. Like if, for example, you've accessed something on a mapped drive before and someone else has it open and it says, well, sorry, you can't save that, it's read-only. In other words, you aren't writing any data whatsoever to that file. It is flat, it is just something that you read the data from and you will never ever change it. A great example of this would be something like an image file, like a texture or something. And so let's assume, for example, one of the compute units needs to read that texture. Obviously, it will never ever write to it. And so that means that the caches themselves won't lose what is known as coherency to one another, because, after all, coherency itself is directly tied to a change in the file. So think about it. Let's say you have level 1 and level 1 cache for the GPU and the CPU, and let's assume that you have a flat file and the CPU reads that file, and then the GPU needs to access it later. I'm just making this up on the fly, of course. And then let's say that the GPU needs to access it, and then later on, say 5 minutes later, the CPU needs to access that file. Well, there's been no change. In other words, there's going to be consistency between the two files because you've never touched the damn thing. Another way for you to look at this is, let's assume that I send you a image via, I don't know, an email, and let's say that image is of a pure white square, just for example, nothing else, just a pure white square, and we both have a copy of that. Then we both have coherency. In other words, both of our files are exactly the same. Let's assume, however, I go into Paint and I draw a little, black dot on it or whatever. My version is no longer the same as yours, and so, if we were to send it to someone else and we would say, okay, this is what the original looks like, just screwing with the guy, then he would be like, okay, well, this is weird because they both look a little bit different. This is a little bit like, I don't know if you guys are familiar with the spot the differences in images, where something really subtle have changed in the image and it's your job to spot what it is. It's kind of similar to this, but in this case, the two images are exactly the same, they're mirrored. I'm really hoping that's, understood. And next, we have what is known as a private buffer. This is also known as a PV. And this will be read and written to by a single thread group. A thread group, or rather obviously, is a group of threads. I'm not going to go too much into that in this particular video. Stuff like that becomes pretty complicated very, very quickly. But access to this also cannot cause level 1 caches to lose coherency. And then you've got what is known as GPU coherent. And this, of course, is all about the compute units. In other words, the compute units themselves read and write directly, and this can be multiple different things, for example, draw calls, or something that's geometry shaders related. Now, importantly, as writing is actually permitted, if you access and then write to something, it can cause level 1 cache to actually lose coherency with the other cache, because, well, as we've spoken about, if you write something, then, well, both are no longer exactly the same copies. Now, the biggest issue in terms of coherency is known as system coherency. And this is actually accessible by both the CPU and the GPU. An example of this would be something to do with CPU and GPU communication. And this actually can cause multiple issues, because obviously the caches, that would be the level 1 and level 2 caches respectively, are the fastest access of memory, others outside of registrars and that type of thing. And obviously, if you started to read and write in this respect, you can actually cause both caches, so that would be the level 1 and level 2, to actually lose their coherency with system memory as well as the various other caches present. So if you think about it, this can cause the most headache in terms of performance loss, because, as just to reiterate, system memory is very fast. Obviously, it's, well, much faster than, say, a hard drive, considerably faster than optical media, but it's still nowhere near the speed of the caches, which obviously are really quick, they're very local, and so generally speaking, you do want to read from the caches because that's the most efficient way of doing it. Generally speaking, the AMD Jaguars actually do have a pretty good hit rate in terms of predicting what data is going to be needed next by the caches, or should I say what data the CPU is going to need next, and so does try to store that in the caches. But obviously, if you've got incoherency between the two data sets, then you can actually have a little bit of a snag. And finally, you've got uncached data. So that's data that's very similar to system coherent. The difference, on the other hand, is, in other words, it's being read and written to by both the CPU and the GPU, so in other words, both are basically molesting it randomly. But the difference is, unlike the previous system coherent one, the uncached was never loaded into the level 1 or level 2 caches of the GPU. So obviously, right then and there, you don't really have issues with coherency, because obviously there was only one copy of them ever, and that was, well, on the main system memory anyway. By the way, these are actually somewhat inefficiency, because what basically happens is that it will continuously have to read the same lines of code, and it will actually have to incrementally update various pieces of code as well, because obviously, pretty obvious stuff, but I'm going to go into it anyway just for a moment. An application is pretty basic in terms of functionality unless it can actually update itself. In other words, it can read and write data. In other words, games, for example, if this is just a pure example, this is by no means getting technical or anything like that, but if you can't update information, and even in something like a fighting game, how can you update the health bar of a character? The same thing, even on using something like Microsoft Word, which a lot of the time I used to take notes and so on. You can imagine that if you actually can't write anything, if the data can never ever change, you're basically just using read-only copies. And so basically programs themselves, they actually have to modify, and this could be done from multiple different things. It could be loops, it can be if statements, it can be based on user inputs, it can be conditional, it can be, just to give you examples of this, it could be everything from you step into a new area to, your health goes lower, whatever. All of these different things make changes to the game's code. In other words, it has to continuously force updates, and this is just a few examples which I'm sure many of you can understand, and I just want to use some simple stuff here just to not overload you guys too much, because we're going to go into the more simpler stuff. Then I'm going to release another video which is going to go into some more in-depth stuff, and we're also going to be speaking not too long, as well as I was saying, in another video that I'm putting up today. I don't know which one's going to be done first, but one of them will be, I'm sure, which is going into the issues with Moore's Law right now. And so I want to really get some of you, because some of you understand a lot of this already, others don't, and so I don't want to really run ahead, because that's kind of unfair, that's uncool, and it's not good for viewership, obviously. So I'm trying to make a video for everyone. It's sometimes a little bit tricky, so yeah, obviously if you know about a subject, however, you don't really need to watch the video, so that's pretty cool. But anyway, moving back on, where the hell was I? Let me see. Notes. Anyway, this uncached stuff will actually be using the Onion Plus bus, and it also has a very similar bandwidth level, similar to the actual Onion bus. So the first three that we've mentioned, which were GPU coherent, read-only and private, just to remind you guys, can be accessed by the CPU, but there are a couple of caveats to remember. The main one is, well, let's just assume, for example, we're copying data to a new location. It doesn't matter what it is, just for the purposes of this. So let's assume that the CPU can actually write this data in an uncached fashion. So in other words, the data itself is completely and utterly uncached on the CPU. And then it can actually flush the GPU caches. So what can then happen is it can then take hold of that memory, through that piece of data, whatever that piece of data is, through, let's say, the garlic bus. And once again, just to reiterate, of course, the garlic bus is the fastest of all the buses, 176 gigabytes per second. And so this is good because of a couple of reasons. Firstly, it's going to be faster for the GPU, to access, because it's no longer going to be restricted to the onion. Now, obviously, the onion is slower. In other words, you're going to be getting slower access compared to the garlic bus. Additionally, it also stops the fact that you're going to be getting the non-coherency issue. In other words, there's no unused, stale, old copies of the data remaining in the GPU's level 1 and level 2 caches, which is pretty damn important. Now, those of you who have been following RGT for a while, or checking out a lot of Mark Cerny interviews, you'll know of what is known as volatile bits and the purposes behind the ability to let me start again with some English. The purpose to actually invalidate certain data on the GPU caches. I'll read you guys out the quote just to refamiliarize yourself with it. Next, to support the case where you want to use the GPU level 2 cache simultaneously for both graphics and asynchronous compute. So out of quote for a moment, that basically means, of course, that you want the level 2 cache to be able to simultaneously store stuff for, let's say, a texture, and let's also assume something like, physics, okay? So back into quote, for both graphics processing and synchronous compute, we have added a bit in the tags of the cache lines, and we call it volatile bit. You can then selectively mark all accesses by compute as volatile. And when it's time for compute to read from system memory, it can invalidate selectively the lines it uses in level 2. And when it comes to write back the results, it can write back selectively the lines that it uses. This innovation allows compute to use GPU level 2 cache and perform required operations without significantly impacting the graphics operations going on simultaneously. In other words, it radically reduces the overhead of running compute graphics together on the GPU. And so, end quote, of course. I can't remember if I said that because I paused to read some notes. And so what will happen is basically the level 1 tags will actually have an additional bit, and it'll be set if the data was loaded from either the graphics coherent or system coherent memory. And so what will typically happen is you'll have the application itself, the application's code, will basically use this to nuke pretty much any of the data there before it does, say, a draw call that it actually accesses one of the buffers. So we've just spoken about the level 2 as well, and once again there has been an additional bit added to level 2, and so the purpose here is that you can actually have it where it can figure out if it was from system coherent memory, and if it does figure out it's from system coherent, then the level 2 can basically invalidate that line, and it can actually write that line back as well. So obviously this allows for much more efficient grabbing of data and basically freeing up the resources as well, so you've got a lot more efficiency there. Now, just to reiterate, the purposes behind all this complexity, as Mark Cerny himself has said, is so that data can much more efficiently be tracked. So whether you've got a texture, whether you've got a compute command, whatever, that data can be efficiently tracked in the buffers, and obviously this rather clearly allows much more efficient processing of their data. In other words, to put it another way, their data can be much more efficiently read, it can be much more efficiently managed, and it's a much faster access as well. It also means, of course, that the level 2 cache, as Mark has said, can be also used for compute. Obviously, there are certain commands, for example, vertex shaders, that type of thing, which are graphics related. But as we've spoken about quite heavily, let's say that you need to do some asynchronous computing using the ACE engines. ACE stands for oh my god, I can't speak today. Asynchronous compute engines, which are ACE, of course. So we've spoken about those, by the way, in another video. I believe it was on the Xbox One versus PS4 GPU, so you can check those out. Sorry guys, I'm a bit low energy, so I'm maybe stumbling a little bit on my words. I can only apologise. But anyway, now remember, Mark and his team have said that the GPU will mostly prioritise graphics. So in other words, the compute, for the most part, will be utilised on cycles where graphics aren't being used. In other words, it will basically use it on quiet portions of the frame. So let's assume that the graphics are running at pretty much full throttle, but, it needs to run a compute command, whatever that is. Now, one issue is we don't want, of course, stale data, because old, invalid data is obviously really bad to process. It wastes a lot of cycles. So you need to make sure that not only are you processing relevant data, but you also don't want any errors processing old data either. And that's where invalidating the cache on level 2 is so important. And so what it will do is basically invalidate level 1 for the graphics and the system, and then it will also, of course, invalidate level 2 for the system coherent. And remember, just to re-point it back out, system coherent is the buffer which is basically readable by the CPU and the GPU. And then it will mosey on to go wherever the heck it needs to go to get the relevant piece of data, because obviously the GPU hasn't accessed that data yet. So what it will do is it will go to, for example, either the CPU caches or system RAM, wherever that data is stored, and then it will get that data, and then it will run that data to do whatever it needs to do. So whether it's moving a crate, whether it's doing something like AI, whatever it has to do. So what it will do then is it will basically perform a write back of the level 2, which will be the system coherent data. So it will basically say, okay, this memory is going to be wrote back to the main system RAM from the caches. I'm hoping that makes sense. The level 2 caches will basically dump it back. It will basically dump back all the dirty bytes, and so now the CPU can see them again. By the way, guys, just to give you a very brief overview of what a dirty bit is, because this is going to risk becoming pretty complicated pretty fast. Basically, the dirty bit indicates whether the block, so in other words, the piece of data itself, has been unchanged since it was actually read from the main system memory, or alternatively whether it's clean. So in other words, you can consider it, okay, well, has it been messed with? If the answer is no, then it's obviously clean, it's clean data. But if the data itself has been tampered with, for example with compute, so let's say the compute has changed something and the data is no longer what it used to be, therefore it's now dirty, so then the system actually needs to correct that. So what's the difference between the earlier, well, the non-PlayStation 4, for example, and, well, the PS4? Well, the difference is that previously the entire complete full version of the level 2 data was flushed. In other words, goodbye. So any data whatsoever, it doesn't matter what it is, it doesn't matter whether it was compute, it doesn't matter whether it was textures, it doesn't matter whether it's geometry, whatever the hell is in that pool of level 2 cache is gone. It's deleted. It's like shift delete. Bye bye. So it needs to be refilled. The difference now is on Liverpool this is not the case. You actually have read-only data, the private data, and also graphics coherent data, so in other words textures and so forth. That remains intact. So in short, let's assume that you have a texture, it was being used, it was a happy smiley face, it doesn't want to be deleted, it likes being there, it's its good friend. Well, on the traditional Radeon structure, it's being deleted and Mr. Texture needs to be reloaded back into level 2 cache. In this case, it doesn't. It's there, it's not been hurt, no smiley faces and textures were hurt in the making of this compute, it's fine. So this has been a pretty lengthy video. There is a lot more to this, unfortunately for me. I say unfortunately because of the ridiculous amount of time it takes for me to actually record these videos, but it's fun nevertheless. I'm learning a hell of a lot actually. So hopefully you guys will stick with me for this and you will enjoy the pain. Anyway, I will see you soon. Take care. Bye for now.